I have 6 of you around. Mami Akusia Debi, Nicole.
Hey. Mr. Diaye Kumase.
Pardon? Agofala. So, Nana Jemfa Akofala Sanam. And then who else? I think 1, 2, 3, 4, 5, 6. Okay, I'm hoping they will join. Nana Jemfa.
Yes, please, Media.
Did you contact what was the name? Your friend, I've forgotten the name.
Edibiano.
Okay. All right, maybe she'll join soon. Okay, so today as I want us to look at Newton's laws of motion. Newton's laws of motion. This morning we looked at it. But the arrangement was to repeat it for those of you who will be coming during the evening session. Okay. So Newton's laws of motion. Let me first ask, what is Newton's first law of motion? Those of you who treated it in school, can somebody state Newton's first law of motion? Yes. Newton's first law of motion. Let me pick the view of Mame Akusia JB. Mame Akusia. Akusia. Can you help us with Newton's first law of motion? Okay. Sanam, help us.
Mr. Diaye.
Help us with Newton's first law of motion.
Okay. It states that a body continues in its state of rest or motion in a straight line with constant velocity unless an external force acts on it.
Good, perfect. So, just as she stated, please, if you are writing, I'll give it to you. So you hold on. So we have the first law. Okay. Second law. And then the third law. But the question is that why Newton's laws of motion? How did it come about? Okay. How did Newton's law come about? Okay. Now, the background of Newton's laws of motion is that over the years, scientists were looking at what actually causes the motion of an object or a body. Okay. So, Hello. Hello.
Mr. Edia.
Okay, so back from the commercial break, I had a network challenge. Okay. All right, but I hope you can hear and see now.
Yes, please.
Okay, so over the years, scientists were brainstorming, sharing ideas to understand what actually causes motion. And so people a lot of scientists express their views. Okay, then the first person who hypothesized or proposed what actually causes the motion of bodies was Aristotle. Then Aristotle proposed that a continuous force on a body is needed to maintain motion. So this was Aristotle's hypothesis or Aristotle's proposal that for an object to move or continue to move, you need a continuous force to be exerted on the body. The question is whether this is true. Is that really the case? All that Aristotle proposes that, you see, for a car to continue being in motion, the engine would have to continue running. The burning sensation of the fuel within the engine block has to be sustained. Now, if that is not done and the engine is stopped, the car stops moving. Please, I hope you are with me. Are you with me?
Yes.
Okay.
Mr. Edia, I'm a bit confused.
Pardon?
So I'm a bit confused. Can you repeat what you said?
What I'm saying is that Aristotle's proposal was that a continuous force is needed for the continuous motion of a body, or for a body to continue to be in motion. Meaning that if the force exerted on the body is not maintained and is stopped, the object cannot move. But what I'm saying is that
Yes, please.
even in our daily lives, there seems to be an application of that source. Or because when a car is moving, when you start the engine, the car, once the engine, continues to stay on, the car can also be in motion. The moment the engine is stopped, the car would also stop. When you are riding a bicycle, as you do the pedaling, the bicycle would continue to be in motion. The moment you stop pedaling, the bicycle will also stop. So daily life activities seems to suggest that, yes, truly, a continuous force is needed to enhance motion. But for an object to stop, it isn't due to the fact that that force which has to be maintained is removed, or is relieved. But an object actually stops due to another force being exerted on the body. And this force, which actually causes an object to stop, even if the force is removed from it, it's friction. If friction is not there, okay, once a body starts moving, if friction is not there, it must continue moving, even when that initial force which pushed it is not there. So, Galileo, another scientist, also proposed that no, it isn't a continuous force that causes an object to be in motion, but it's rather an object, okay, moves. An object would move when a force is exerted. What he's saying is that you need a force to start a stationary object to move. So this is Galileo's proposal. So Galileo's proposal, and he is of the view that a continuous force is not needed to sustain the motion of a body. But rather, a force is needed to cause a stationary body to move. So this was his first proposal. 2, a force is needed. A force is needed to stop a moving body. To stop a moving body. And 3, a force is needed to change the velocity and the direction of a moving body. So all that Galileo was saying is that, yes, it's true, you need a force, okay, to start a stationary body to be kept in motion. Yes, it's true, you need a force, okay, to stop a moving body. And yes, it is true that you need a force to change the velocity and direction of a moving body. But you don't need a continuous force to keep the body in moving. So all that Galileo was saying that, yes, once you apply force to start these things, the body will continue being in motion. So in his experiment, all that he did was to throw an object in the air. So when you throw an object, you give it an initial force. It will keep moving. It will keep moving, even though the initial force is removed. So you give it, and it has to be kept in motion for some time before it stops. Okay, so all that they were saying is that you don't need a continuous force to keep an object in motion, but you need a certain amount of force to start when the body is stationary and to stop it. So rather, a body stops not because the continuous force is removed, but a body stops due to the exertion of friction on the body. If there's no friction, the body would have to continue being in motion for some time. And a typical example of this proposal is that, you see, when you skate on ice, it's rather unfortunate here we don't have ice. There's no winter, so we don't have ice. But if you are skating on ice, okay, and you give yourself an initial push, because the surface of ice is frictionless, you can move on and on and on and on and on till you find yourself off, okay, off the surface of the ice. Please, is that okay?
Yes, please.
Good. So this way, Aristotle's and Galileo's proposal of what actually causes forces. Is that okay? So Galileo is simply saying that if an object is stationary and there's no force on the body will continue to be stationary. It can only move when a force is exerted. And if a body is moving and there's no force acting against it, it will continue to move. Okay. But then these proposals is hardly to experiment on the surface of Earth, because hardly can we get friction-free environment on the surface of the Earth. If you experiment with the ground is full of friction. If you experiment with the air, there is huge air resistance, which is also friction in air around. So these things can hardly be experimented on the surface of the earth. Then my friend Newton comes in to put all the ideas together, okay, thereby linking the relationship between forces and motion. So his first law actually establishes the relationship between force and motion. His second law establishes how to measure this external force which causes motion. So let's look at Newton's hypothesis of what actually causes motion, hence Newton's laws of motion. So over the years, as Aristotle, Galileo proposed something on motion, he comes in later to put all the ideas together, and now he's the father of motion. He's now the father of motion. So Newton's first law of motion. His first law of motion says that a stationary body will continue to be at rest until an external force is exerted on the body. That is first part of his first law. The first part of the first law. A stationary body will continue to be at rest until an external force is exerted on the body. Then the second part is that a moving body will continue to be in motion with a constant velocity until an external force is applied. So that's the first law. It's made up of two parts. Meaning, if a body is at rest, okay, it will continue to be at rest. Or when a body is in motion, it will continue to be in motion with a constant velocity until an external force is applied on the body. Okay, all the two parts of the motion tells us that you will need an external force to change the direction or to change the state of a body, whether at rest or whether it is moving. And this were taught. Hello, are we okay?
Mr. Dia,
Yes.
please, how does light come into the whole discussion of the motion?
I've not talked about light.
Yes, I missed that part earlier.
No, I haven't talked about light.
Yes, please.
Now, what is the second law? So, okay, before we move on to the second law, the first law of motion is also referred to as the law of inertia. So Newton's first law of motion is also referred to as the law of inertia. Okay, the first law is also known as the law of inertia. Now the big question is, what is inertia? What is inertia? Objects naturally opposed to the change in state and the change in its velocity. Okay, so when I'm there and then you push me, okay, what are you doing? You are changing my state. Maybe I'm stationary. You want, as you exert force on me, you want me to start moving, and object naturally will resist it. If an object is at rest and you want it to move, what it implies is that you want to change its velocity, and objects naturally would resist that change in state or velocity. And this is what we mean by inertia. So we define inertia Inertia is defined as the opposition or the reluctance of a body to the change in velocity of a body. So is the reluctance of a body to change to a change in velocity of the body. Or you can, instead of reluctance, you can use the opposition of bodies to the change in velocity of the body. That is inertia. Inertia of a body is directly proportional to the mass. So inertia of bodies is directly proportional to the mass of bodies. The greater the mass, the greater will be the opposition to the change in velocity. That is why when a body, to have somebody who is so fast to be running, then you need extra push to the body to change its state of running, slow running to fast running. Okay, so the greater the mass, the greater will be the body's natural opposition to the change in velocity. The lesser the mass, the lesser will be the force that has to be applied to change the body's velocity. Okay, that is why we refer to the first law to be the law of inertia, because the first law is that a stationary body, will continue to be stationary unless an external force is applied. Now, if the stationary body has a greater inertia, that is greater mass, then more or larger force will be required to change the body's state of rest to a state of motion. Now, if the body is already in motion and the body has a greater inertia or greater mass, then more force has to be applied to stop the moving body to come to a stop. To enhance the moving body to come to a rest or stop. So the first law is also referred to as the law of inertia. Please, are you okay? Guys?
Mr. Dia, please, the board is a little bit blurry, so I can't see well.
Please, is it a general problem to all of you?
Yes, please.
A little bit blurry.
Yes, please.
So do I restart? Or is it because of the lights? Deborah, is it fine? Is it fine? I'm repositioning it. Is it better?
Not really.
Oh, it is.
Mr.
It is.
Dia, please, can you take a shot?
Okay. Hello, to the rest of you, is it better?
Not really.
Hey, it is. Oh. Okay, then please let me restart to see if I can fix the problem. Okay. All right.
Yes, please.
It's a network problem and hardly can I fix that part of the problem.